And then we're going to divide that by a sub n. So that's multiplying by the reciprocal. So that's n factorial. All right. And then we just want to simplify this. So let's see how we can do this. How can we rewrite n plus 1 factorial? So that would be n plus 1 times n, and then times n minus 1, and then times n minus 2, and so on, right? 5 to the power of n plus 1 is just 5 to the n times 5 to the first power. Okay, and then here we have 5 to the n, and then n factorial is just n times n minus 1 times n minus 2, and so on. Okay, so this is what we have so far. So now you can see what cancels out. So you have this going away with this, and then you have the 5 n's going away. So that will leave you with just n plus 1 over 5. And then we have to take the absolute value and then take the limit as n approaches infinity. So what do you get here? Right, you get OO. Correct, very good. But what does this say about your series according to the ratio test? Right, you get div. So remember that the ratio test says if the limit is greater than 1, then it's divergent. So here it is greater than 1, so we can say this is divergent. Okay, so that's that. All right, that one doesn't seem too bad. Let's try the next one. Okay, so here's the next one. Let's use blue. So again, we're going to do the ratio test. So it's going to be -1 to the power of n plus 1 over n plus 1 squared plus 1, and then multiply by n squared plus 1 over -1 to the n. Okay, so here's your ratio. And then let's see what simplifies. So I think for this one, you don't really have much to simplify besides the negative ones. So we are going to have this cross out with this, but that'll leave you with -1 to the first power. So we have -1 n squared plus 1 over n plus 1 squared plus 1. And yeah, I don't think you could go much further than that. So when you take the absolute value, well, when you take the absolute value, the -1 in the front goes away. So this is just going to be the same thing, just without the -1. Okay, so from here you can take the limit. So when you take the limit as n goes to infinity, what do you get here? Yeah, you get 1. And very quickly, why do you get 1 again? In terms of the same power. Yeah, so the numerator has a degree of 2, and then the denominator, well, when you multiply out the denominator, you also have a degree of 2. But so yeah, they have the same degree on the top and bottom, which means you can just take the coefficients, right? So the coefficients will end up being 1 over 1, which will just be 1. So here the limit is 1. Okay, what does that tell us? So according to the ratio test, what does the limit of 1 say? So yeah, ratio test says if the limit is 1, then it's inconclusive. So the ratio test failed here, unfortunately. But that's okay. So we just need to use another test. Looking at this series here, do you guys think you would, you have a suggestion as to what other test we should use here? Yeah, alternating series, right? Because there's a negative 1 to the end. So this is definitely an alternating series. Yeah, let's try that. So let's just pull up the alternating series. Actually, you know what? Does anyone remember how the alternating series tests work? I'll pull that up anyways. Yeah, so you find b of n, and then what do you do with b of n? So here it is. Check to see if the limit goes to 0. Yep, and then you have to make sure that it's also decreasing, right? So let's do that. Okay, so this is the work for the ratio test, which failed. So let's try again with the alternating series test. So here, b of n is just 1 over n squared plus 1. Limit of b of n as n goes to infinity. Here, is it 0? Yes, it's 0 because the denominator gets bigger. And then is this decreasing? So 1 over n squared plus 1. Yeah, I think this one's obvious enough that it's decreasing, right? Because as n gets larger, then the denominator gets larger, so it's definitely decreasing. So decreasing. So we can say that this is convergent. Okay, so that's all we have for the ratio test. What do you guys think? Do you guys like this test? It's pretty good. I don't know. Do you guys think one of the tests is like, do you guys dislike one of the tests? We still have about, well, we still have one more to go. So, but yeah. Yeah, the majority of the tests, they have a tendency to like if they fail, you have to use another test. There's only like like one or two tests that were like you don't have to. I don't remember what they were though. I have to look at the definitions again. But let's go back to the PowerPoint because we just have one last test. Here it is. So we just did these two examples. All right, so the last test is called the root test. This test is pretty much the same as the ratio test. So if you look at the conclusion, it's exactly the same. So if the limit is less than 1, it's convergent. If it's greater than 1, it's divergent. If it's 1, then it's inconclusive. So the only difference between the root test and the ratio test is that instead of taking the ratio of the next term over the previous term, you're just going to take the nth root of a of n. Okay, so yeah, that's pretty much the only difference. Let's look at some examples as to when the root test is used instead of the ratio test. That was on the test. What was on the test? There was a square root. Yeah, there was a square root sequence, but the root test is for series. So you couldn't have used this on a test. Okay, so take a look at these examples. Let me just switch to the board. Okay, so I'm just going to copy down the part we have to calculate because the conclusion is the same as the ratio test. Let's use green. So we have to take the nth root of a sub n. So let's go ahead and do that for the first example. So here's a sub n, which is just n to the nth power over 3 to the power of 1 plus 2n. So if we take the absolute value and then take the nth root, what do you get? So let's refresh everyone on how to deal with these exponents. So when you have the whole thing raised to an exponent, you can sort of just distribute the exponent to the numerator and denominator. So it becomes the following. N to the n times 1 over n divided by 3 to the power of 1 plus 2n times 1 over n. Okay, so you're able to do that. Then when you simplify, let's see what you get. So this will just be n to the first power, which is just n. And then on the denominator, let's simplify the exponent. So it'll be 1 over n plus 2, okay? So that's what you get. Let me just give you guys a moment to process that. And then, yeah, this is as simplified as it's going to get. So let's go ahead and take the limit as n approaches infinity. What do we get here for the limit? infinity. Is that right? So the numerator goes to infinity. The denominator becomes 3 to the, well, the 1 over n goes to 0. So it's 3 to the second. So it'll become this. Yeah, that's infinity. Okay. Yeah. So what's our conclusion here? Remember that this test has the same conclusion as the ratio test. So if you remember the ratio test, diver, yeah. So this is divergent. Okay. All right. Let's try the second one. So here is a sub n. Just copy it. We are going to take the nth root. So absolute value, and then take the nth root. Well, in this question, all that does is it sort of gets rid of this exponent here, along with that exponent. So this becomes 5n minus 3n to the third over 7n to the third plus 2. And then, yeah, that's pretty much it. So let's take the limit of that. Let me move this over just so you guys don't confuse the work. Okay, so limit as n goes to infinity. What do we get here for the limit? Yeah, so it's -3 over 7 because the degree on the top and bottom are 3, so you take the leading coefficients. So this will be absolute value of just -3 over +7. And then we take the absolute value, it's just 3 over 7. So what's our conclusion here? Convergent, yes. Okay. All right, last example. So for this one, same idea. We're going to take the nth root. So we will have -12 to the nth power over n, absolute value of that, and then take it to the nth root. So this becomes absolute value of just -12 over n to the 1 over n. Okay. Now, when you take the limit, let's see what happens. So when the limit as n goes to infinity, the numerator is just -12 because there's no n there. So it just stays as -12. The denominator, what does the denominator become? So it's n to the power of 1 over n. Yeah, 1, right? Because the exponent is approaching 0, and then anything to the 0 power is 1. So this becomes just 12 after you take the absolute value. So this is divergence, right? Okay, so yeah, that's pretty much the root test. Very similar to the ratio test. Any questions so far? You just raise this one over n, take the limit. Yeah, so yeah, basically, that's all the root test wants you to do. Shouldn't 12 be convergent? Um, Let me just pull up the conclusion for the root test, which is the same as the ratio test. Screen. So here's the root test. The conclusion is like this. So if the limit is less than 1, it's convergent. If it's greater than 1, it's divergent. And if it's 1, it's inconclusive. I think you're confusing it with like the other situation where like if you get a number, it's finite and therefore convergent. But but yeah, as far as like the ratio and root tests, you have to stick strictly to how they were the conclusions, which might be different than like the stuff we've done before. So it can get a bit confusing. What does one here mean? Yeah, so one here means it's inconclusive. If you think about it in terms of like the ratio test, if the ratio turns out to be 1, that means that as you go further into the series, your 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 terms start to be the same, and therefore you don't know whether that converges or diverges. Let me see if I can give you an example. So if the limits of a sub n plus 1 over a sub n equals 1, that means as you go further and further into the series, you might get something like this. So you might get 0.5, 0.75, 0.9, 0.99, 0.999, and then 0.999. So in this case, you can see that the ratio is slowly becoming 1, right? Because if you take this over that, that's really close to 1. So this particular series here is inconclusive because we don't know if you add all these, whether that'll converge or diverge. And I mean, if they're all positive signs, it's probably going to converge. But let's say it was alternating, then then it might like converge or diverge. We don't know. So that's why when the for these tests, when the limit is 1, we don't know what it actually does, whether it converges or diverges. But yeah, as far as like these problems go, you don't really need to think too much about it because like I said this many times, but it's not a proof course. So if you look at the proof, it might become very intuitively obvious as to like why this is the conclusion. But for now, just make sure how to go through the process. Like it's pretty much mindless here. But yeah, well, what I will say is that it's good to know when to use each test. So let's go back to the examples that we just did. Here. So let me ask you guys this. Do you see any similarities between these three examples? Or in other words, like what characteristics about these three examples make it so that the root test is very convenient? Variable in the exponent for numerator and denominator. Yeah, that's pretty much the main idea. So these three examples, they're given in such a way that when you take the nth root, you get something very nice. Like it simplifies something very nice when you take the nth root. So that's really the reason why the root test is very convenient for situations like this. Okay. All right. So that's pretty much it. Uh, next, we'll talk about a strategy you can use for deciding which test to use for a particular problem. So, all right, let's look at this. So it's basically like a checklist. Number one, I always recommend you to just try the divergence test. That should be the first thing you should always try because number one, it's easy. And then if it works, then you can just stop right there. And if it doesn't work, then you didn't really waste too much time. Okay, so that's the first thing. Is always try the divergence test. Then number two, so if it looks like a p-series, so 1 over x is some power, or if it, you know, if it looks like it but it has some extra terms to it, you can sort of strip out those terms. So when you can do that, then it's probably a comparison test problem. Okay. If it looks like something that you can integrate, then try the integral test. Yeah, so if you look at some series, you can sort of see how you can do like a u substitution, then it's probably an integral test. And then next question, does it look like the form of a geometric series? So if it does, then you can get it into that form and then observe the common ratio, okay? And then last but not least, actually, no, wait, this is number 5. So number 5 says, is it an alternating series? So if it is, try the alternating series test. And then this is the last one. So if it contains any factorials or constants raised to a power, then you can try the ratio or root test. So that's basically what we've been working on in this section, right? Those are stuff that have like 3 to the n or n factorial, things like that. You shouldn't be too worried about this because for exam 2, we pretty much cover like most of these situations. For exam number 3, you're only going to get like situation 5 and 6 here. So you guys shouldn't be too worried about this. But this is just like the big picture. Okay, yeah, so we're done with these convergence tests. We finally did them all. There is one test I will mention. I don't know if any of you guys have ever heard of it. It's called the limit comparison test. And I'm not going over that. I decided not to go over that, mainly because that test is one where if you can use that test, there's almost always another test that you can use in place of it. So I'm not going to go over that one. But yeah, how do you guys feel about finally learning all the tests for convergence? You feel great. Yeah, it is a lot. All right, anyway, so on your free time, you can try homework 5.4. There is also a quiz that covers sections 8.1 to 8.4, so do that as well. I don't think there was too many questions on it. So yeah, that's it for 8.4. Let's move on to 8.5. Okay, so 8.5 is power series. What do you guys know about power series? It's a series. Yes, very good. Anything else? It includes powers. Yeah, probably. It's a power series. All right, that was just no. Okay, so let's learn what a power series is. So in prior sections, our definition of series was just a sum of a list of numbers, right? So a power series is pretty much the same thing, except now instead of adding numbers, we're going to allow our series to include variables. So yeah, that's basically a difference. So it's not just numbers now. Now there's like x's and stuff, which seems pretty scary, right? All right, so here's the notation. Um, let me just read this. So a power series about A, or just power series, is a series in the following form. So summation n starts at 0 to infinity of c sub n times x minus a to the nth power. So that's the general form. And then let's just go through what all the letters mean. So a and c sub n, those are just going to be numbers, okay? So when you're given a problem, c sub n and a are going to be actual numbers. And then x is going to be the variable. Right, so the answer to a power series is not actually a number. It's going to be like just a bunch of x's and stuff. That's correct, yeah. So the c sub n, so the thing in front of the parentheses, we refer to those numbers as the coefficients, which should be intuitively obvious. And then the number a, so x minus a inside the parentheses, the number a, that is usually what we refer to as the center of the power series. So that's kind of why we call it a power series about a. So the number a is the center, and then c of n are the coefficients. All right, so next let's look at some examples of power series. So some of them can look fine, some of them can get pretty complicated, but they all have the same general format. Okay, so let's look at the first one. First one we have, I'll read the summation part first. So summation as k starts at 0 of 2 to the k power times x to the k. So if you were to expand this power series, you would get the following. You would get 1 plus 2x plus 4x squared plus 8x to the third plus 16x to the fourth. Okay. So this is a power series. Can you guys see what the coefficients are for that series? The first one? 2. Well, focus on the left-hand side of the equation. So if you were just on the left-hand side of the equation, what are your coefficients? Yeah, powers of 2, right? So particularly 1, 2, 4, 8, 16, and so on. Those are your coefficients, right? But if you want to think of it in like the right-hand side of the equation, the coefficient is 2 to the k, right? So that's like your c of n part. And then we have x to the k power. Do you guys see what the center is for this series? So what is a in this series? Yeah, it's 0. Do you guys all see why it's 0? Yeah. So let me just write that out just so we can have everyone else see it. Go here. So this is technically just 2 to the k power x minus 0 to the k power, right? So a is over here. This is a. So your center is 0 here. All right. Let's look at the next power series. So the second one, what is your what's your coefficient for the second one? 1. Yes. So the coefficient is 1, right? For all of them, you can see it's 1 here. There's also 1. There's a 1, which means there's also 1 here. And then, what is your center? 5. Did you type that before I even asked the question? Yeah, the center is 5. So this is A, which is your center. Okay. All right, and then let's look at the third series. So focusing on over here, guess what I'm going to ask you guys? What is the meal you had for breakfast? No, I'm just kidding. So yeah, what's the coefficient and what is the center? Yeah, so 1 over k plus 1 is the coefficient. You can see that here, here, and then here, and then here, and then here, and then -3 to center. Yeah, so this is x minus -3, right? So -3 is your center. Okay, so hopefully this clears it up on how a power series is written. Some examples of power series. Does the sign of for the a value matter? Yes, it does matter. So a power series is in the form x minus a. So it's like this, x minus a, which means in the second example, a is 5. In the third example, a is -3. So yes, it does matter. All right, moving on. So naturally, the next question is, well, for every series we looked at whether it converges or diverges. So what about for a power series? So the answer is it depends. It depends on what value of x we use for the power series. So if we use a particular x value, it might converge. If we use another one, it might diverge. So what do I mean by that? Well, the easiest way to explain is through this example here. So consider this power series, which is x to the n, right? That one's a relatively simple power series. So let me write this out. So here we have the power series x to the 0 plus x to the first plus, let me switch it, plus x squared plus x to the third and so on, right? So this is this power series. But depending on what we plug in for x, it might give you a convergent or divergent series. So if we let x equal 0.5, you're going to get 0.5 to 0 power 0.5 to the first power plus 0.5 squared, and so on and so on. And then if we let x equals 2, you're going to get a different series. You're going to get 2 to 0 plus 2 to the 1 plus 2 to the 2 plus 2 to the 3, and so on. And it turns out that um, the first one is convergent, and then this one here, the second one, is divergent. So the convergence of a power series depends on what value of x we use, okay? All right. Let's see what else is next. Okay, so there is a list of x values that will make the series convergent. In fact, it's usually in an interval. So the interval of x values that make the power series convergent is called the interval of convergence. So that's a new word or new phrase that we will learn. And then um, this interval of convergence is usually written in interval notation. So then once you have that, there's also this thing called the radius of convergence, which is basically half of the length of your interval of convergence. Okay, so let's use the same example just to show you how these two terms work. So the power series x to the n, the interval of convergence happens to be -1 to 1. Don't worry about how we got that, just accept it as fact for now. But what that says is that if you choose any x value between -1 and 1 to plug into the x for the power series, it will give you a convergent series, okay? And if you choose anything outside this interval, it will give you a divergent series. So that's the interval of convergence. And then because our interval is from -1 to 1, our radius of convergence is 1 because this interval has a length of 2, and then half that length is 1. So radius is 1. So is it clear so far what all these things mean? Does anyone want to ask anything? You guys are all good for now? All right. Can you explain why the interval converges is -1 to 1? Yeah, I said don't worry about that for now. We'll learn how to find the interval convergence later. Can't we use the root test to find the interval of convergence? Yes, it's coming up. You're spoiling it. Right now, I'm just making sure that everyone knows like what all these words mean. So, yeah. But everyone seems fine. So let's move on. Okay, so we said that there are certain x values that will make a power series converge. So there's a special case where if you let the x value equal to a, so if you just let the center equal the x value, that will always give you a convergent series. So yeah, here's a proof. I pasted it because it was very short, but let's go back to the previous examples. So, all right, let's look at these three examples again. We said what the centers were, right? So for the first one, the center was 0. So if I let x equal 0 for the first series, that will give you a convergent series. And then if you let x equals 5 for the second series, that will give you a convergent series as well. And then likewise, if you let the third series have x value of -3, that will make it convergent. Essentially, the reason why it becomes convergent when you plug in the center as x is because the parentheses part goes to 0. So that's why it becomes convergent. Do you guys see that, by the way? Like if you plug in a particular x value that makes the parentheses go to 0, then sort of each term just sort of goes away. So that's why when x is equal to a, it's always convergent. Okay. Yeah. All right. So that's that. Next, we will find out how to find the interval. So here it is. Yeah, Alice, you were right. So to find the interval of convergence, there's usually only two tests that we do. And it's always going to be the ratio test or the root test. Yeah, so when you use the ratio test or the root test, you will get the interval of convergence, but there's one issue, and that's with like the endpoints of the interval. So when you get your interval, say it's like -1 to 1 or whatever, you're not going to know whether the endpoints are included in the interval of convergence. So you'll actually have to test those separately. Okay, and to test those, just use whatever test seems appropriate. So yeah, let's jump right into it. So here we have a power series. We're just going to do 3 examples today and then leave it at that because this is quite a heavy chapter, but I made it very light. So taking a look at this power series here, let's just make sure we know what's going on. So I can list out the terms if I wanted to. It would be it would be 7 times -1 to the first power times 1 times x to the first power plus 7 -1 squared times 2 x to the second power. And all right, I don't want to go anymore. But that's how the power series looks like. Can you guys identify the coefficient part and the center of this power series? Yes, so center is definitely 0, right? Because x to the n is basically x minus 0 to the n. So a is definitely 0. What would be your coefficient? Yeah, so the thing in front is your coefficient. This whole thing is your coefficient. All right. So I would say to find the interval of convergence, 75% of the time is usually ratio test. So I would say always try that first. And if that doesn't work, then try the root test. So let's see what happens if we try the ratio test. So a sub n is this. Right? And then a sub n plus 1 is this, to the n plus 1, and then n plus 1 here, and then x to the n plus 1. Now we have to take the limits, or actually before that, we have to take the ratio. So let's see what happens. So here's the ratio. You want to see if you can simplify anything. So let's see. The 7s go away, right? This -1 cancels out with this -1 to leave you with just -1 to the first power. X to the n cancels out with this x to the n to leave you with just x to the first power. And then I think that's it. So let me just carry everything else over. Just the n here. Yeah. Next, let's take the absolute value. So when you do that, you will get just x to the n plus 1 over n. The absolute value just makes the -1 go away. Okay. Now we need to take the limit. So let's go ahead and do that. All right, so here's something new. When you're taking the limit as n approaches infinity, so notice how our expression here has two variables. It has x and it has n. So because our limit is regarding the variable n, you can actually take the x out of the limit. So what I mean is you can do this. You can write x on the outside here, and then write the limit part. And the reason you're able to do that is because the limit doesn't depend on x, which is why you can factor it out. Okay. By the way, what's the limit here? As what's the limit of n plus 1 over n? It's 1, right? So yeah, we have 1 here, which just simplifies to absolute value of x. So all right, there we go. There's our limit. But then you might be asking, well, okay, our limit is absolute value of x. What does that even mean? Yeah, so do you guys think you know what's the next step? We got a limit. You thought the limit would be a number because that's what it usually is, but it's not a number, it's a variable. Solve for x. How so? So we're not going to actually solve for x here. What we're actually going to do next is keep in mind what test we're using. So this is the ratio test, right? Let me pull up the ratio test one more time just to have it for reference. Isn't X a specific value? No, it's not. Remember, a power series is a series that has variables in, like, as part of the series. So X is not a particular value. But our limit is X. But remember what the ratio test states as the conclusion. So the ratio test states that if the limit is less than 1, then it is convergent. If it's greater than 1, then it's divergent. So our limit is X. What do you think we should do next? And also keep in mind that the directions of this question was to say, find the interval of convergence. Do we sub for X? Not quite. So we're trying to find what X values this power series will converge. But the ratio test says it will only converge if the limit is less than 1. So what do you think that means? Zero to 1? Almost. All right, this is what we're going to do, guys. So here's the answer. The ratio test says that it's going to converge if the limit is less than 1. So what we're going to do is we're going to solve for when the limit is less than 1. Okay, that's what we're going to do. So how do you solve this inequality here? So this inequality, how do you solve it? You can. You need to split it into 2 different parts, if you remember. Yeah, essentially what happens is the first part becomes X is less than 1, but then the second part is X is greater than -1. Yeah, so if we were to draw that on a number line, let me move this. So let's say here's the x-axis of all your possible x values. So here's 0, here's -1, and here's 1. Yeah, so what we've just found out is that if you choose any x value between -1 and 1, and you plug that in as your x value for the power series, you will get a convergent series. And the reason why it gives you a convergent series is because these x values make it so that the limit of the ratio test is less than 1. Okay, so hopefully you guys saw what just happened. It's kind of like doing a lot of things at once, or applying a lot of things at once. But yeah, that's how we use the ratio test to find the interval of convergence. So the interval of convergence here is from -1 to 1. So -1 to 1. Yeah, stop me if you guys have any questions. But we have our interval. The only question is, for this interval, do we use parentheses or do we use brackets? Right? That's the only question left. parentheses. How do you know? Not inclusive. But why? Because that's what we use for an inequality sign. It's yeah, so be careful. So if you let x equals -1 or 1, these are the x values that correspond to this case of the ratio test. So in those cases, it's inconclusive. So you can't just say like it's parentheses or brackets without actually testing it. So in order to see whether it's parentheses or brackets, you actually have to plug these endpoint x values into the power series and then go from there. So we're going to do that now. Here's your series. So if we let x equal, say, -1, we will get the following series. This will be 7 -1 to the nth power times n -1 to the nth power. So this is the series you get if you let x equals -1. The question is, does this converge or diverge? Let's simplify this. How can we simplify this thing here? So do you see why this and this would just cancel out? Yeah, so -1 to the n, that's either going to be -1 or +1, right? So if they're both positive or both negative, they're always going to multiply to +1, so they just go away. So this is just the series 7 to the n. So the series 7 to the n, is that convergent or divergent? Yeah, that's definitely divergent, right? So if you have x equals to -1, that gives you a divergent series, which means in our interval of convergence, we should use a parentheses here. Okay. And then we have to test the other endpoint. So was a series earlier inconclusive? You mean this one? Remember, the convergence of a power series depends on what x value you use. So when we ran our test, we found out that this power series converges if you use x values between -1 and 1. But we're just testing the endpoints now. Yeah, so we're not done yet. So letting x equals 1, we're going to get the following series. We're going to get 7 to -1 to the nth power times n to the 1 to the nth power. 1 to the nth power is nothing. So this is just 7 times -1 to the n. Is this convergent or divergent? So if I list out what this series is, this is, well, n starts at 1 to infinity. So when n is 1, we get -7. When n is 2, we get +7. And then -7, and then +7, -7. Is this convergent or divergent? Um, well, this is actually divergent, and the reason I believe this is divergent is because what's the divergence test? Yeah, it's divergence test. So if you take the limit of this expression here, you're not going to get 0. So therefore, it's divergent by the divergence test. It seems a bit misleading because it seems like the sum might be 0, but you can't really do it like that. So yeah, this is divergent. All right, so we found out that the endpoints are both divergent, so this is also a parentheses. So here is your interval of convergence, means letter I. So the interval of convergence for this power series is -1 to +1, not inclusive. Okay, so yeah, that's one example. Yeah, it is tough. You're using basically like an idea from the previous chapter with a new thing. So yeah, you will have to get your head around it, but I think eventually you guys should get it. All right, let's do another example. So we just did that one. Let's try this one. The radius of convergence. Oh yeah. So I forgot about that. Let me go back. Here. So our interval of convergence was from -1 to 1. So what is your radius of convergence there? It's just 1, because the distance from -1 to 1 is 2, and then half of that distance is 1. Yeah. Okay, so let's try this example. Okay, so this is a power series. It says determine the radius and interval of convergence. So again, this series will converge depending on what x values we choose, right? So we have to find the interval of convergence. In other words, the list of x values that will make this series converge. We don't know what they are yet, but we have to find it. So we start with the ratio test. So we're going to find the limits, right? Once we find a limit, we have to set the limit to be less than 1, because if the limit is less than 1 for the ratio test, that means it will converge. So let's find a limit here for the ratio test. This will be, let me just write what we're doing, ratio test. So we're going to have x minus 5 to the n plus 1 divided by n plus 1 to the 4th plus 1 times the reciprocal, and then x minus 5 to the n. So simplifying this, we get just x minus 5 on top times n to the 4th plus 1 over n plus 1 to the 4th plus 1. Okay, now we need to take the absolute value, and then we need to take the limit. Okay, so the x plus 5, I can pull that out because that doesn't depend on n, so that can come outside the limit. So x minus 5. Wait, why did I write it over here? Okay, so let's pull it out here. So I can pull that out. And then just focusing on the limit. So the limit of that expression, what does that become? Should be 1, right? Because the degrees are the same, so you just take the leading coefficients, so it's just 1. So it's just 1 times the absolute value of x minus 5. Okay, so we found the limit. This is L, right, the limit. So our limit for the ratio test is absolute value of x minus 5. What should we do if we want to find where this series converges? So keep in mind the conclusion of the ratio test, where we just did the ratio test and we found the limits. According to the ratio test, what is the requirement for it to converge? So the ratio test states that it only converges if your limit is less than 1, okay? Which means we need to figure out where is our limit less than 1. So we need to solve this inequality here. So solving this inequality gives us x minus 5 is less than 1, and then x minus 5 is greater than negative 1. So this gives us x is less than 6, and x is greater than 4. I think that's right. Negative 1 plus 5 is 4. Yes. Okay. Yeah. So if we were to draw a number line, let me use a line tool. Perfect. And then we have 4, 5, 6. So we know that this right here from 4 to 6 is our interval of convergence. So if you write I can say it's from 4 to 6. But the question is, does it actually converge on the endpoints as well? So at 4 and at 6. We don't know because those are where it's inconclusive according to the ratio test. So we have to test it. So going back to our original series, which is this thing right here. We'll have to test the endpoints now. So let's test x equals 4 first. So if you let x equals 4, you will get the following series. You will get 4 minus 5 is negative 1 to the n. And then that's n to the 4th plus 1. Is that conversion or divergence? Can you guys see whether that converges or diverges? I think it should be quite alternating series test, right? I think this converges by the alternating series test because b of n is this, and this decreases and goes to 0. So I think this is convergence. Yeah. So this is convergence, which means 4 gets a bracket, and then let's test 6. So let x equal 6. This gives you 1 to the n. Well, 1 to the n is just 1. And then n to the 4th plus 1. Does that converge or diverge? Yeah, I think that, wait, convergent. Why do you say convergence? Yeah, but this one isn't an alternating series anymore, so you can't really use that test. The divergence test. Divergence test says if the limit doesn't go to 0, then it diverges. But here the limit does go to 0, so the divergence test fails on this one. So this one is actually a comparison test. So you can compare it to 1 over n to the 4th, right? And n to the 4th, do you guys remember what that does? Yeah, so that converges. So yeah, so this is also convergent, which means this gets a bracket as well. Okay, so there's that one. The interval of convergence for this power series is when x is between 4 and 6, inclusive this time. Also, notice something. So do you guys see what the center is for this power series? It's 5, right? So notice how the interval of convergence is always like symmetric about the center. So it goes from 4 to 6, which is symmetric about 5. And we also said that it's always going to be convergent when x is the center when it's at 5, which is included inside. So that makes sense. What's the radius of convergence here? Yeah, it's 1, right? Because distance from 4 to 6 is 2, and then half that distance is 1. Okay, so that was another example regarding interval of convergence. Any comments so far? Because I feel like you guys never have questions. Yeah, honestly, I think the most tedious part about these questions is the testing the endpoints. I feel like that takes the majority of the time because you have to tap into your memory of like what's an appropriate test for that particular endpoint. Any other comments? All right, if there's no comments, then let me just summarize the process a little bit. So we're given a power series. It will only converge on particular x values. We don't know what they are, but we can find what they are. So to use a ratio test, you want to make sure that the limit of the ratio test is less than 1, right? So what you do is you go to your power series and you do the ratio test. Once you find your limit, which for a power series is not going to be a particular number, it's going to be something regarding x. Once you find your limit, you set it to be less than 1, and that will give you the interval that it converges in. And then once you have that, you just test the endpoints, okay? So hopefully you can wrap your head around it a little better this time. Let's do one more example. And then after that, I have some important announcements that you want to stick around for. So stay tuned. All right, last example. So this one right here. Okay, so this one is actually one where the root test seems a little more appropriate. Do you guys see why? Yeah, so both the numerator and the denominator, they're raised to the power of n. So we should use the root test here instead of the ratio test. So let's go ahead and do that. So the ratio test says that the limit is the absolute limit as n approaches infinity of the absolute value of not the ratio, but the nth root of whatever you get. So the nth root, just like that. Okay. And then let's simplify this. So this is limit as x goes to infinity. When you take the nth root and simplify it, you get x minus 6 over n. This is the root test. Okay, so we can pull the x minus 6 out because it doesn't depend on the limit of n, which I should have wrote here. So this is as value of x minus 6 limits as a value of 1 over n. Okay, what's the limit here? Yeah, it's 0, right? So we get 0 times absolute value of x minus 6, which is 0. So recall that the root test has the same conclusion as the ratio test, which means to find the interval of convergence, you do the same thing. You have to set it less than 1. So less than 1. All right. Can you guys solve for x now to figure out the interval of convergence? So we want to solve this inequality for x. Why are you guys looking at me like that? Yosef, is something bothering you? No, so x minus 6 times 0 is just 0. So this is what we're left with here. Would the value of x matter? Aha. So yeah, as you can see, there's no x here. So we can't really do anything. Well, you have 0 is less than 1. Is that even a true statement? Yeah, so this is true. Do you guys remember what it means when you get a true statement when you're trying to solve an equation? It means it works. Infinite, yeah, it meant infinite solutions. I don't know if you guys remember that, but it's not false. But when you're trying to solve like a system of equations or whatever, and you get a true statement, what it means is that every single possible value of x is an answer. So since we got 0 is less than 1, which is a true statement, what this means is that every single value of x will make the series converge. So the interval of convergence is actually negative infinity to infinity. Okay. In other words, it doesn't really matter what value of x you plug into this power series; it'll always give you a convergent series. Okay, so I don't know if you want to do the radius. It's still infinity because like half of infinity is still infinity. So yeah. um, there are cases where wait, actually, never mind. I was gonna say something, but I forgot what. Um, so yeah, this is the root test, and this is a situation where everything converges. That's all the examples we have. Do you guys want to ask anything or comment? You guys good? Yes? Okay, thank you. So I have some announcements. Let me just go back. So um, I'm not going to assign any more homework from now on because I've looked at the homeworks that are remaining inside Lumen, and they're getting a little ridiculous. I can't lie. Like they're really hard, and they don't really represent like what like how things should be. So here's what I'm gonna do. You can do the homework if you want, but I'm not grading it anymore. So everything behind 8.4, so like 8.5 all the way to the end, I don't really care if you do it anymore. You can do it for practice. Definitely try it if you like, you don't understand anything, but I'm not assigning it anymore. So there's that. Second thing I want to talk about is the schedule for exam 3 and the final. So do you guys know when the last day of class is? Okay, so um, I've pulled up the schedule, and you guys should write this down. So the last day of class is December 8th. So that's the last day we have class. No, exam 3 and the final are two different things. Yeah. And then they released the final schedule. So our final is actually on December 15th. So that's when our final is. So last day of class is December 8th. And then our final is on December 15th. I'll probably email you guys all this information, but I'll just say it now just in case. I don't know. So yeah, looking at the schedule from now until December 8th, so we only have like 5 more lectures. So do we submit the final same as before? Yeah, yeah. The final will just be like all our 3 exams, so it'll be the same. I probably think that the exam will be, well, first of all, we're definitely not going to finish the syllabus because there's just no way. If you look at the syllabus, let me pull it up. Yeah, hold on, give me a second. So here's the syllabus. Where are we right now? We are on here, 8.5. Is it the departmental final or one of yours? It's gonna be mine. I don't know if they always done it like that, but this semester they said there is no uniform final, so I'm making my own final. But we are over here right now. Exam 2 is here. We did this. Now we're here. Look at the topics we have left. So we have 1, 2, 3, 4, 5, 6. There is no way we're going to do 6 topics in like 5 lectures, especially when we still have exam 3 and we need to review for exam 3. So what we're going to do is we're probably going to end at like maybe over here, 8.8, and then we'll just have our 3rd exam. So a little more information about the final is that what I'm planning to do is just like take questions from the 3 exams and just put them on the final. That's what I plan to do. So so there's not going to be a review sheet for the final because your 3 exams will be a review sheet. So I'm going to pick various questions from the 3 exams that I've given and just put them on the final. So that's what I plan to do. But yeah, that's basically what I wanted to announce. I don't know if you guys are okay with that. The same question, well, not exactly the same. Like, I'll definitely change the numbers. Yeah, not like the same question, but like if I pull out the geometric series problem, it's still going to be a geometric series. So yeah. Oh yeah, next week is Thanksgiving. Okay, great. So we have even less time to do this. So we're probably going to cover even less material. But yeah, that's basically the plan. So the exam, the 3rd exam is probably going to be a last day of class, and then the final will be on the 15th. So yeah, just a little update on like how I plan to finish this. Yeah, so that's all we have for today. Hopefully you guys are okay with the material so far. Have a good weekend. I'll relay this information through email. So
Do we meet next week? You said no, right? Sorry.
what's that?
Do we meet next week?
I honestly don't even know, but like I'm sure someone will let me know.
All right.
Yeah.
Have a good weekend.
Yep.
Wait, James, I just want to clarify it. So the homeworks are not like mandatory from now on, basically.
Yeah. So everything from 8.5
Mhm.
and after that, I don't really count anymore.
Got you. Hey, you're blessing it, bro. Thank you, appreciate it.
Regarding the chapter that might be missing, may I contact you about final so we can learn about those? Yeah, definitely. Yeah, I know a lot of you guys, probably going on to higher level math courses, so you'll need some of these topics. So yeah, I'll definitely I'll work something out with you so you're not missing those topics when you move on to other courses.